drawing like we did in our previous graphing activity for stoichiometry. We want to start with a balanced equation as always. This time we're going to react hydrogen and nitrogen gases to produce ammonia, which is NH3. Okay, these are both diatomic gases. So we'll make it H2 and N2. So to balance this out, put a 2 in front of NH3, and then a 3 in front of H2. What we need to do in order to start this off is start with 12 molecules of hydrogen and 5 molecules of nitrogen at reaction 0, and then we'll go one reaction at a time through 4 reaction events. Okay. I'm going to color code these and make it key. My hydrogens are going to be red and my nitrogens are going to be blue. Make sure when we're drawing these diatomic molecules that they are 2 particles together. Okay, so I'm going to start with my 12 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 5, 1, 2, 3, 4, 5 nitrogen. In order to go through one reaction event, we're going to need 3 hydrogens and 1 nitrogen. So I just like to circle mine up. That's 1 reaction's worth. Each reaction is going to make 2 ammonias. So I'm going to start by drawing those 2 ammonias. There's NH3s. There's 1, 2, and then I can draw everything else that's left over. So I'm going to wind up with 9 hydrogen particles left. Nine, and then 4 nitrogens. Okay. We go through another reaction event. We're going to take another 3 hydrogens and 1 nitrogen. So there's another group. We'll make 2 more ammonias for a total of 4. 1, 2, 3, 4. And then be left with everything else. In this case, that's going to be 6 remaining hydrogen molecules. 4, 5, 6. And then 3. Maybe let's go 3 there. Nitrogen. Another reaction event. It's going to take another 3 hydrogens and 1 nitrogen. Let's maybe go down here. 3 and 1. For a total of 6. 2, 3, 4, 5, 6 ammonias. And then we'll have to make sure we're following conservation of mass, drawing everything that's left over, which is going to be 3 more hydrogens and 2 more nitrogens. 1, 2. Because we're making more ammonia and have fewer reactant molecules left, these are a little spread out. So I'm just going to circle these individually. 1, 2, 3 hydrogens and 1 nitrogen. So what we're going to wind up here in our final box is 8 ammonias and 1 nitrogen left over. This is different than our previous graph that we created in particle diagram because we had both reactants run out at the exact same time in this case, or in that case. In this one, there's 1 nitrogen molecule left. There's 1 nitrogen molecule left. Okay, so if we look at these all together, we're going to see this. Now, reaction 5, I know this is question number 5, but if we look at reaction number 5, what's it going to look like? It's going to be the same thing, right? And that's because there's no hydrogen left. It all ran out. So there's no way to create more ammonia because the hydrogen is all used up. Okay. Now, there's a word for the fact that there's nitrogen left over. If it's left over after the reaction or there's more than enough, what do we call it? Excess reactant. So the nitrogen is going to be the excess reactant. And we're going to call hydrogen the limiting reactant. Okay, so if we go through and we graph this, we're going to get a graph that looks like this. Okay, we're going to see that the nitrogen and hydrogen amounts are declining as the ammonia amount is increasing, and it stops at the point that the hydrogen runs out. Okay. What that tells us is the hydrogen limits how much product can be formed. It limits how much product can be formed. I had a student also say that they thought maybe limiting reactant meant that there was a limited amount of it. That's another way of thinking of it. Okay, there's a limited amount of it, so it determines how much product can be formed. Okay. So if we look at the BCA table question, remember we're going to just make this really simple in our BCA table to start out with our equation. Let me get nice and zoomed in here. 3H2 plus N2 yields 2NH3. And then this is just particles to start out with, right? We had 12 particles and 5 particles with 0 particles of our ammonia to start out with. Okay, we know we're going to form and we're going to use up so we can add our plus and minuses. So based on what we have from our graph, we know that all of the hydrogen got used up. So we're going to subtract all 12 particles and be left with that number of moles. That is what determines the ratios of change for all of the other reactants or products. Okay, so we already knew that we used up 4 of these particles and we were left with 1. And then we wound up forming 8 particles of ammonia. The limiting reactant, which I'm going to label again, I like to always label mine somewhere in my table. I usually like to label them above my equation. I usually put LR in a circle over my limiting reactant and excess in a box over my excess reactant. The limiting reactant tells you which amount of change is going to take place, how much you form and how much you use. So I'm just going to take one of these as an example. If we didn't already know from our particle diagram, we could figure out how much change occurs using a ratio. So we could say how many moles, really, of NH3 are going to be used when 12 moles of hydrogen are used. If we know from our reaction that 2 moles of ammonia form every time 3 moles of hydrogen are used. So then we'll solve for our x, right? 12 times 2 is 24, divided by 3 is 8. Oops, equals 8 moles of NH3, right? And that's where that change comes from. So that's where we're headed now, is into stoichiometry and BCA tables where we know both amounts of reactants and we have to figure out which one gets used up. So we'll start by looking at this at the particle level and then we'll add in the math for the BCA tables.